Question 1 is about exponential and logarithmic functions. If you have an exponential function, it's going to be some number a raised to a power that contains a variable in it. So x is a member of the real numbers. The base a must be positive and not equal to 1. If you keep raising 1 to a power, it's not going to change. So let's just take a quick look at the graphs. If your value for a is greater than 1, that means that, first of all, anything to the 0 power is 1, so they're all going to go through here. But if your base is greater than 1, that means as you move to the right, your graph is going to increase quite quickly without bound. And as you move to the left with those negative exponents, they're going to send your base and the exponent into the denominator. So it's actually going to get closer and closer to 0 here on the left-hand side. Now, domain on this is going to be set of all real numbers. Range on this is going to be from 0 to positive infinity. Now, if your base happens to be between 0 and 1, some small fraction, it's actually going to flip your graph over, because when you raise a fraction to a large power, then it's going to make your number increasingly small. So again, they all go through 0, 1. So on this side, you're going to approach 0, and on the other side, the negative exponent is going to flip him over, so now all of a sudden, it's going to grow without bound. Okay, again, this is going to have the same domain and range as the a value greater than 1. So Euler's number, and I'm not too concerned about you knowing this piece, but you need to have a pretty good idea of what the value of E is. And Euler's number, just like pi, is an irrational number. Its value we use is 2.718. We round it. The derivative of a function f of x equal to e of x, so it's an exponential function base e, is itself. So you take the derivative of the e to the x, and it's actually e to the x. If you have a composite function where there is something other than a plain old x up in the exponent position, then you take the derivative of the e to the expression, e to the expression times the derivative of the exponent there, the expression for the exponent. Then that would be your chain rule. So then if we're asked to differentiate, then we have 4e to the x power. Oops, let's do it this way. F prime then will be 4 times the derivative of e to the x, which is just e to the x. And then if I do the derivative of x itself, it's just 1. So it's going to be 4e to the x. If I do the derivative of e to the 2x, the derivative of e to the power is e to the power times the derivative of the power, so times derivative of 2x, which is 2. So 2e to the 2x. If I do the derivative of this next function, then we're going to have to use addition and subtraction rule along with our chain rule for our e. So g prime of x will be 3x squared, and then minus 5 times the derivative of e to the 2x, which is e to the 2x, times the derivative of the 2x, which is just 2. So this will be equal to 3x squared. 2 times 5 is 10, so minus 10 e to the 2x power. All right, for our next example, we have a quotient, so we're going to have to use quotient rule. So g prime of x will be equal to bottom, x to the 6th, times the derivative of the top, so e to the 3x power times the derivative of 3x, which is 3, minus the top, e to the 3x power, times derivative of the bottom, which is going to be x to the 6th, so 6x to the 5th, all over the bottom squared. Okay, let's go ahead and simplify this. So let's factor out the common factor. We have a 3 that we can factor out. We have a x to the 5th power that we can factor out, and an e to the 3x that we can factor out. So we're going to have 3 e to the 3x, x to the 5th power times, to get x to the 6th, I need one more x and everything else I have here. So x minus, in order to get a 6, I'll need a 2. I have the e to the 3x, and I have the x to the 5th, all over x to the 6th squared, power to a power you multiply, so it's going to be x to the 12th. And our last step here is going to be to reduce. We will cancel 5 of these with 5 of them, leaving us with 7. So now this is going to be 3e to the 3x times x minus 2 all over x to the 7th power. Next example is product rule. So we're going to have first, let's do f prime of x. First would be x squared plus 3x minus 9 times derivative of the second, which is e to the x, plus the second, which is e to the x, times derivative of the first, which will be 2x plus 3. So then let's go ahead and factor the e to the x out. E to the x times x squared plus 3x minus 9 plus 2x plus 3. And combining like terms, it will be e to the x times x squared plus 5x minus 6. Okay, we have one more. Again, we have a chain rule going on here because this is e to the square root of x minus 4. Get it to, there it goes. All right, so then dy dx will be equal to e raised to the power, so e raised to the square root of x minus 4 times the derivative of the square root of x minus 4. So it's going to be 1/2 times x minus 4 to the negative 1/2 power times the derivative of the inside, which is just 1. So let's clean this up. We've got e to the square root of x minus 4 in the numerator and 2 times the square root of x minus 4 in the denominator. Okay. It says that more Americans are buying organic fruit and vegetables and products made with organic ingredients. The amount, A of t, in billions of dollars spent on organic food and beverages t years after 1995 can be approximated by the function A of t is equal to 2.43 e raised to the 0.18 t power. Estimate the amount Americans spent on organic food and beverages in 2009. Well, first of all, let's figure out how many years after 1995 2009 is. So 2009 minus 1995, 14 years. So then A of 14 will be equal to 2.43 e to the 0.18 times 14, which is 30.2 billion. It's a lot of money. Okay, and then in part B it says estimate the rate at which spending on organic food and beverages was growing in 2006. Okay, the rate of growth is going to be equal to the slope of our tangent line, so let's go ahead and get a derivative. So A prime of t will be equal to 2.43 times the derivative of e to the power is just e to the power, times the derivative of the power, which is going to be 0.18. Okay, and then when we multiply these two numbers together, it's 0.4374 e to the 0.18 t power. So now they want us to figure this out for 2006. So 2006 minus 1995 means 11 years passed. So then A prime of 11 will be 0.4374 e to the 0.18 times 11, which is equal to approximately $3.17 billion per year. And that's an increase because it's a positive number. So that's the rate of growth 11 years after they started this, keeping track of this with this formula. All right, so we have one more problem here. A company's total cost in millions of dollars is given by this cost function, where t is the time in years since the startup date. Find the marginal cost. Okay, so then marginal cost is going to be our derivative. So C prime of t will be equal to, derivative of 200 is 0, so it's negative 40 times e raised to the negative t power times the derivative of the negative t, which is going to be negative 1. This is, I said 40, I wrote 4. Okay, negative 1 times negative 40 is positive 40, and if I want to move this e to the negative t power into the denominator, that will turn his exponent positive. B says find C prime of 0. So C prime of 0 will be 40 over e to the 0 power. Anything to the 0 power is 1, so this is just 40. So in our case, it's in millions of dollars, so $40 million. Part C says evaluate your derivative for 5. So 40 over e to the 5th power is approximately $0.2695 million. All right, part D, find the limit as the cost function approaches infinity, or time approaches infinity, and then find the limit of the derivative of the cost function as t approaches infinity. And why do you think the company's costs tend to level off as time passes? All right, so then for part D, let's do this part first. The limit as t approaches infinity of the cost function, which is 200 minus 40 over e to the t power. So your denominator is going to be growing without bound as your numerator remains constant, which means that second term is going to 0. So 200 minus 0 is going to be 200, and it's million. As far as the derivative goes, limit as t approaches infinity of 40 over e to the t power will be equal to 40 over infinity, which is 0. Okay, so then the marginal cost is going to 0 while the total cost is approaching 200 million. Okay, so then as you're selling more and more, your cost is approaching a certain number, you're starting to divide those fixed costs up among infinitely many items, then, or infinitely many of whatever that you're doing, then it's going to level out for you.